We'll probably be a minute or two late, but
I think we just be ready to start our time.
Oh yeah, there's slide trail. So I yesterday when we practiced, and I think it's looked fine. I think I can just I think we got to the point where the way we're supposed to say this right there. So yeah, it's easier practice. If you guys are okay with that. We're going to be trying to realize that.
Why don't we go ahead and start? And just a word of warning, you probably noticed, students in the class, that if somebody joins us on Zoom, you'll have to admit them into the room. So that message will pop up and you'll just hit the admit button. Well, to our guests,
Noel, just so you know, I've already joined. This is Steve Casey, formerly with Eagle.
Yes, I'm aware of that. Thank you, Steve.
Okay.
So we've got two guests on Zoom at the moment, including Steve Casey from Eagle, as he just announced, and evidently one of your parents. I don't know which one. So anyway, to our guests, I'd like to welcome you to the senior design presentations this morning. Students have worked hard all term. This project is a little different than some in that it's a possible problem that people have been aware of for some time. And it's a problem that's not unique to the single location that the students will talk about today. Although for the sake of design, we have them focus on a single location. Mine drainage is a common issue virtually everywhere we have mining operations, and the Keweenaw is no exception. There's mine drainage to the south of us in iron mining regions. There's mine drainage issues in the west, in the Rocky Mountains in Alaska. It just is one of these common problems, and there are unique problems and difficult problems to solve. The challenge with this particular one is the mercury, which requires that the treatment reduce mercury concentrations to an extremely low level in order to meet the water quality criteria. So the students had quite a challenge in analyzing treatment technologies to find one capable of doing that, and then to design a system in the time constraints that they have that would provide full treatment and discharge and meet all the requirements of the course. So I don't want to steal any more of their thunder. With that, we'll introduce Team SNASS here. The first team is going to introduce the specific site and the problem and their portion of the task. Team SNASS.
Good morning, everyone. We're SNASS Consulting, and this is our senior design project on Camel Creek's mine drainage, remediation, environmental assessment. My name is Stephanie Clayson.
I'm Adam Poulter.
I'm Sarah Berry.
I'm Sadie Johnston.
So to orient ourselves where the problem is we included a map of the Keweenaw Peninsula, which includes the mine drainage location near Calumet. We also included Torch Lake and Michigan Tech. So to give a little overview of the site history, the Osceola mine was created in 1873 by the Osceola Mining Company. In 1895, there was a fire that broke out in the mine, actually becoming the deadliest mine disaster in the copper country history. Most of the casualties occurred in shaft number 4, and we've included a diagram of 6 of the 11 total shafts of the mine. Fast forward to 1968 with the closure of the mine due to a labor strike. After that, all of the shafts were presumed to be capped until leakage was discovered at shaft number 4. and also high concentrations of dissolved solids and metals such as mercury. So because of that, Hamel Creek was added to the 303 D list for impaired waters, and a TMDL was created in 2002 to try to reduce that mercury pollution by 99%. However, nothing has been done to mitigate this to this day. We also wanted to include a list of stakeholders we feel would be impacted by this problem, such as the Keweenaw Bay Indian communities, Torch Lake Pack, Eagle, amongst others. So here's our entire project layout, including some important components such as the testing locations where we tested 4 locations with water quality parameters. We also included all of the accessible culverts where we sampled flow.
All right, so now that we have more of a background of our issue, these are kind of our major objectives of our project. First, we were tasked with performing a characterization of the hydrology of the Hamel water system. And then we were also tasked with performing our environmental assessment for the observed Hamel Creek mine drainage. We were also tasked with assessing the extent of the mercury pollution at the mine drainage, because that is a crucial factor for regulatory treatment operations. We were also tasked with determining the optimal location for the proposed treatment operations. And these are just kind of a list of different tasks that we've done throughout the project. We did some water testing of collected samples from Hamel Creek to determine things like mercury concentrations and conductivity. We also did flow rate sampling along different locations for Hamel Creek to get a good idea of how flow rate occurs throughout the system. We also did a watershed and wetlands delineation to outline kind of the boundaries of the water system. And then we also did a leak analysis and included analysis of the different permits that are necessary for this project. And then to get a better idea of flow rate, instead of just measuring, we also did some mathematical estimations. And this includes the end member basin analysis, and we also did a Michigan regression equation for NRE.
So to go into some specifics of the methods used throughout the project, for the wetland and watershed delineation, it was necessary to use GPS delineation and ArcGIS mapping, which we'll go into later. And then for the sampling, which we did through Whitewater Associates, we used a dirty hand, clean hand system, which also incorporated a double bagging system. And for those that are unaware, this method basically entails 2 people, one of which is actually holding the sample and taking it as the clean hands person. And at no point are they actually touching the outer bag, which is the responsibility of the dirty hands person, which is responsible for taking this bag between the cooler and the sampling location. While we took these samples, we also used a conductivity probe to detect the conductivity. And before these samples were shipped out to the lab, we used a Michigan Tech facility to filter these samples. And through this process, we used both glass filter and nucleopore. The anions for this case were water washed through glass fiber, and the cations were passed through a acid washed nucleopore, and then the mercury were pre-soaked acid wash nucleopore. And then also during that time, we took flow rate calculations using a metal rod with a turbine on the bottom. And then with electronic devices, we could count the amount of times that turbine spun in a minute. And using that data, along with the depth and width of the stream, we were able to calculate the velocity of the water. And then that data was used with combination of the historical data to use in the EMMA and MRE analysis.
Social wetland delineation, we did a visual delineation of the water bed and riparian immersion. We didn't find the total area to work sure the extent of how far upstream and downstream along Hamel Creek we needed to go for each of the design option. But the wetland delineation is important since those regulations may become important to the U.S. Army Corps of Engineers, the DNR, and Fulton County. And then what watershed delineation was formed by taking high points of interest above the mine drainage and then connecting those points perpendicular to the contour lines. The watershed area was 1.8 square miles. This is just under 2 square miles, which is the EPA required area for a permit. So we're just under that. That's a high.
So to go into the specifics from the lab data that we recovered, it should be noted right off the bat that in 2002, when the DEQ did these samples, the mercury levels were measured at around 130 nanograms per liter, which were used in some of the other groups' data. But when we did these sampling, we actually found that the highest was 38 nanograms per liter at the mine drainage site. And it also should be noted that all 3 sites that we tested was over the chronic limit of 1.3 nanograms per liter. Even the upstream location, which we weren't sure at the time whether this would be the case or not, but through the testing, we discovered that it was. Also, the chloride levels at site 1 exceeds the chronic limit. And as you can see through the table, that level was 300 milligrams per liter. The presence of other anions such as calcium and magnesium should be noted as well, since that impacts some of the other consulting firms' results. This goes for the other trace metals as well.
So field measurements were taken at the accessible culverts along Campbell Creek. This is done because measurements and dimensions can be easily taken. Using a continuity equation, we found velocity using the meter and area of the culverts to find the flow rates. Measurements were taken in September, October, and December. Those measurements, using some historical data provided by Dr. Urban, we made a monthly hydrograph. Using that data and interrelated data, we found that the average annual flow at Chickens Grove was 2.05 feet per second.
So in addition to doing measured flow rates, we also did calculation-based flow rate estimates. And for those of you who are kind of unfamiliar with the economic data analysis process, it's basically using a simple mass transfer equation and conservative tracers along the water system. The conservative tracers that we use in this analysis are conductivity, calcium, magnesium, sodium, and fluoride. And for the 2 dates that we had comprehensive data, which was October 27th and December 3rd, we have our resulted data in table 4. As you can see, the October 27th flow rate results are actually negative. And this is because the flow rates that we measured on sites 3 and 4 for Highway 26 and Gregory Road, the flow rate actually decreased as we went downstream, which is not naturally supposed to happen. So that actually created negative flow rate results at the mine drainage. But for December 3rd, we had a little bit better results. Those were all positive, and the average value we got was 1.063 cubic feet per second. But that was the only data that we had really for flow rate estimates. So we also did some analysis with just conductivity as the tracer, and we also included the Tecumseh Road location to provide better results. Oh, can you go back actually? So our resulted flow rates were 1.48 cubic feet per second, 1.26, and 1.02 between October 27th and December 3rd. And then we also created a monthly hydrograph of the mine drainage, and this produced an average annual flow rate at the mine drainage of 2.37 cubic feet per second.
We also used the Michigan Regression Equation, or MRE, to both double check our results from the EMA and to have another set of data. For those of you that are unfamiliar, the MRE is a equation developed specifically for the Michigan area by environmentalists who went through multiple Midwestern states to drive these equations and develop a way to estimate peak stream flow using a variety of Bayesian characteristics. As you can see through the table, some of the ones that we used was the slope the percent of forested area throughout the stream, and various others like the average 24-hour rain depth. And it also should be noted that all these values for the coefficients we're taking for a 10-year peak flow. And all in all, this resulted in a peak stream flow of 10 years of 2.8.
So for our design element, we created a decision matrix to determine which location along Camel Creek would be best suited for construction of a water treatment facility. We looked at a variety of factors at 3 sites, and these factors included property values and land availability. And for these 2 things, we took into account the other consulting firm's sizing to make sure that those would fit into the land that was available. We also looked at flow and mercury concentration, and for both of these, we preferred lower values because that would both reduce the size needed and also costs. And finally, we looked at permitting. A variety of water resource permits such as floodplain and wetlands were taken into consideration. So this is our decision matrix here. We used a ranking system of the factors to determine the weight that each of the factors had in the final decision. So in column C, you can see the ranking of those factors. 3 indicates that it is the most important. So for ours, that ended up being land availability, flow, and mercury concentration. In the other 3 columns, each of the 3 sites were ranked according to how well they met those factors. A 3 being, again, it met those considerations very well. Those 2 columns were to multiply together to create a total score at the top. A high score is preferred, so the drainage site was our recommendation with a score of 26.
So I'm not sure ways to consider. There was a beaver dam between Tennessee Road and the line drainage outlet. This created some issues. It disrupted flow rate measurements. And also it may be the reason why accumulated mercury and conductivity levels were found upstream. Although these were currently there, they're not considered permanent throughout the research of us and other consulting firms. In October, one of the beaver dams was removed, as shown in the picture. Previously measured flow rate of mine drainage was 2.5 liters per second, and this was measured by the DEQ 2002. And there's TMPL, which is fairly similar to what we provided. But seasonality was not taken into account due to time constraints, since we only worked on this project in the fall, and also the historical measurements that were used were also data that was taken in the fall.
So just to wrap it up a little bit, so the treatment facility we determined would be best suited at the mine drainage, that would be the optimal location. And then for the flow rate measurements and calculations we performed, we had an overall range of 1.02 cubic feet per second to 2.82 cubic feet per second. And that's also summarized in our table over there. And then as far as water quality, there was elevated mercury levels at each site, but as Steph just mentioned, they could be due to beaver dams or other factors. And then this is a big concern though, the elevated mercury levels, because it poses a significant health risk, not only to aquatic life, but also to human health, as excessive consumption of this of fish that have mercury poisoning that could be potentially harmful to humans. But as far as the next step goes, we would want to work with the other consulting firms to implement the optimal treatment operations at mine drainage. And then in order to incorporate a better range of flow rates, we would want to include or incorporate for seasonality. And in order to do this, we would consider implementing the flow gauge stations along Camel Creek, because this would provide a more complete set of flow rates for them for their design operations. But before we actually end things here, we want to throw out some acknowledgments. One to Dr. Noel Irvin for his continuous guidance and assistance throughout our project, as well as to Michigan Tech University itself for providing the field equipment and financial support for this project. Yeah, if you guys have any questions, feel free.
Question.
Yes.
So if I understand correctly, you did the watershed analysis, like for the peak discharge of the 2-acre watershed to which the mine drainage contributes, right?
Correct.
And that would be like the total discharge you would be designing your treatment system for another TP plan.
Yeah, the point of interest was slightly downstream of the mine drainage outlet at Quincy Road, so it incorporated upstream of Elm Creek and the mine drainage.
And then your estimated, of course you couldn't be out there through the whole year, but your estimated hydrograph, the shape of that is different than local streams, right? Which peak in March and April typically. So why do you think that was, or can you explain that?
I did find that too. Inflated data was found between about January to July, so we didn't have any data between there. We just knew that in January, February, be low, and then peak up. We just kind of used the trend line to with our data. So more data would have to be found to get a more accurate estimate of that.
Seems like there must be more groundwater contribution or something. There's a lag there from the peak stream flow would be the snowmelt occurs a bunch of people. So this mine drainage could be 2 months later. It's just interesting that there's that lag. Thanks.
I wonder if you just clarify the reason for using the end member mixing analysis. What does that tell us that we can't get otherwise?
It provides a better range of the conservative tracers throughout the watershed. Theoretically, they're supposed to provide accurate estimates of the mine drainage flow rates. So, yeah, and then using multiple conservative concentrations gives us a little bit more of the variability in the flow as well.
Any other questions? All right.
Did the conservative tracer concentrations vary over time from the mine drainage?
Your estimate that varies over time, the conservative concentrations.
The tracers, the conductivity, for example, that's probably what you had the most measurements of. Was that a constant in the mine drainage, or did that vary over time?
Again, we were limited just based on seasonality of having only be able to do it in the fall, but throughout our multiple days of testing it, it seemed fairly consistent.
Okay.
Thank
you.
The historical data we do match up pretty well to current data, at least with conductivity measurements. Yeah.
Other questions, Steve?
No, thank you.
Well, thank you then, team. Now, give me just a minute to do a transition here.